Hello and welcome back to Eigen Akademie. In our last video, we introduced the idea of physics as a way of modeling nature, and we also looked into the importance of units, measurements, and dimensions. And today we are ready to take our journey deeper into this world. So the first thing we are going to address right now is the physical quantity. What is it really? So a physical quantity is something that can be used to describe any physical phenomenon, and also it should be measurable, so quantified. And from this we can construct a definition for the same, that is, any number which is used to define a physical phenomenon in a quantitative manner is called a physical quantity. For instance, we have time, length, mass, electric current, and so on, and by these we are referring to measurable properties of the real world. Now for some quantities like time or length, we define them operationally, that is, we specify how to measure them, and that alone forms their definition by the operation of measurement. You can measure time using a stopwatch or by using the periodic oscillations of cesium atoms in an atomic clock. Length could be measured using a ruler, and so on. There are other kinds of physical quantities which require a conceptual or derived definition that is based on how systems behave rather than on direct measurement. Right? So these can be defined using axioms, models, or derived relationships. For instance, let's think about mass, or rather inertial mass, and this is defined based on inertial resistance, how an object resists acceleration. Similarly, force, we can infer it from how mass behaves under acceleration. And even energy, like kinetic energy, which is given as half mv squared, it is a concept derived from conservation laws. So we see that two kinds of definitions emerge, that is operational and conceptual. Moving on, let's look at the different types of physical quantities. So the classification here is done in two main ways. Firstly, on the basis of their mathematical representation. So we have the numeric type of quantities, and these are just plain numbers with no units. Mostly we'll be seeing things like ratios over here. For instance, we can have refractive index or relative density, specific gravity, and so on. Then we have scalar type of quantities, which are magnitude only quantities that do have units, and they just don't care which direction you're measuring them in. So we have mass, distance, speed, time, work, energy, so on. Then of course we have vectors, which are quantities having both magnitude and direction, and they always need a unit. So let's look at this example of a box on the ground with both normal and frictional forces acting on it. Now the total force acting on it will not be just the sum of these two together, as the direction needs to be taken into account. Lastly, we have tensor type of quantities. So these are generalizations of vectors to higher dimensions, and they of course have magnitude, units, as well as directions. So what these do is basically extend vectors to higher dimensions. And for instance, we have electric current, or actually rather electromagnetic field tensors, and stress, moment of inertia, and so on. Next, we look into the second type of classification of physical quantities based on their role in physics. So here we can have two types of physical quantities. Firstly, the base or fundamental quantities, and secondly, derived quantities. So the fundamental quantities are independent, which means that you cannot define them using other quantities. And so we have time, length, mass, electric current, temperature, and so on. Now derived quantities, on the other hand, are constructed from combinations of other fundamental quantities. So you have velocity, which is length by time, force, which is mass times acceleration, or pressure, which is force upon unit area. These, as you can see, are thus dependent on the fundamental quantities. Now let's look at a fun exercise. Given a set of physical quantities, can you tell if they're dependent or independent? What you'd have to do in order to find that out would be to check if any of the physical quantities in a given set can be constructed from the remaining ones. You can pause here if you'd like to try this out on your own. Okay, so the first one, we cannot construct force from length or time, so it's independent. Second, we can construct force from mass and acceleration, as it is mass times acceleration, which we have already discussed. Hence, this is dependent. Moving on to the third one, acceleration, as we know, is length by time squared, and this too is thus dependent. Next, mass, length and velocity. Well, no, we cannot construct any of these from the other ones. And the last one, momentum. Yes, momentum is a product of mass and velocity, so this would be dependent. So now that we understand physical quantities, the question arises, how do we measure them? And this is where units come in. So units of measurement should be accurate, and they should also be stable or reliable and universal. So like observers in different locations all over the world should be able to reproduce or duplicate the same standards of measurement. Historically, standards of measurement were very physical, so to say. Let's take the meter for example. So in 1791 it was defined as 1/10,000th the distance from the North Pole to the equator. And later scientists created a physical bar of platinum iridium stored in Paris, and that was the meter literally. Time, similarly, the second was once defined as a fraction of the Earth's rotation, and the kilogram was based on a platinum cylinder kept under lock and key. But there are limitations when using physical artifacts to define standards of measurement, as these can change or degrade over time and with temperature. So we moved on from units being defined by objects to being defined by fundamental properties of nature. The second, for instance, is now defined using the vibrations of a cesium-133 atom, precisely 9,192,631,770 cycles of microwave radiation between two energy levels. Similarly, length is now defined according to the speed of light. So a meter is how far light travels in 1 by 299,792,458 of a second. And the kilogram is now defined by the Planck's constant using something called the Kibble balance. Alright, so now let's look at systems of units. There have been different systems over time: FPS, which is foot pound second, CGS, centimeter gram second, and MKS, meter kilogram second. But today, we primarily use the SI system, which is built on 7 base units. So basically this takes upon the MKS system and modernizes it by adding further units and refinement. So let's quickly go over the SI units. We have the meter, which is the unit for length, the kilogram, unit of mass, second, unit of time, ampere, unit of electric current. Then we have Kelvin, which is the unit for temperature, mole for amount of substance, and finally candela for luminous intensity. And every other unit can be formed by combining these. Before we proceed any further, there are two other units worth mentioning, and these are the supplementary units for measuring the plane angle and the solid angle, and both of these are dimensionless. The radian is the angle made at the center of a circle when the arc length is equal to the radius. It's a clean geometric way of thinking about the angle and naturally emerges in calculus, in rotational motion, wave physics, and so on. Essentially, it's the ratio of the arc length to the radius. And here you can see how it changes with the arc length. The steradian is the three-dimensional analog of the plane angle. It's the unit for the solid angle, and you can think of it as light spreading in space or flux radiating from a point, and it is given by the ratio of the area to the square of the radius. The degree is another unit for measuring plane angles, and here you can see its relation with the radian. So 1 radian is 180 over 2 pi degrees. An interesting result which arises from solid angles is the relation between the cone half plane angle alpha and the solid angle omega. Basically, let's say this is the cap of a cone and we are given the plane angle for this cone as alpha. So how can we get omega from this? Now the relation here is that omega equals 2 pi times 1 minus cos alpha. Let's actually go ahead and derive this now. Let's assume that we have a right circular cone with its apex at the center of a sphere, just like in the previous image, and the cone opens up with half angle alpha, intersects the sphere of radius r, carving out a spherical cap. Now at an angle say theta, we can look at it right here. For a small change in angle, say by amount d theta, we can have this thickness of area right here as r d theta, as given here, and the height of this from the axis would be given as r sine theta. You can work this out. So the differential area which we would get from this would be given as 2 pi r squared times sine theta d theta, and if we integrate this area from angle 0 to alpha, we would basically end up with a equals 2 pi r squared times 1 minus cos alpha, and from the definition of solid angle we can thus obtain the result that omega equals 2 pi times 1 minus cos alpha. Alright, so now moving on from SI units, there still remains something vital that we need to discuss, and that is unit prefixes. So this is basically a specifier added to the beginning of a unit of measurement to indicate multiples or fractions of that unit. These standardized words, which represent powers of tens, also help us to think across scales, from the quantum to the cosmos. For the last part of today's video, let's look at some special units that show up in various areas of physics. So firstly, we already saw the plane angle can be described in radians and degrees. Now a degree can be divided into 60 arc minutes and 1 arc minute into 60 arc seconds. And thus we can define 1 arc second in terms of radians, and this would be equal to pi over 3600 times 180 radians. Next, let's look into some special units of length. First, we have the light year, which is basically the distance that light travels in 1 year, and so we can calculate it from its definition. So we can obtain 1 light year equals 9.4607 into 10 to the power 15 meters. Then we have the astronomical unit, which is basically the average of the maximum and the minimum distances between the Earth and the Sun. So 1 AU equals half of the sum of R max and R min. So you can basically see it in this picture here, and putting in the values of those radii, we can get 1 AU equals 1.496 into 10 to the power 11 meters. Then we have the parsec, which is the distance at which 1 astronomical unit subtends 1 arc second. And so here again we can see this from the diagram. We have this circle and we have this arc here. Say it is equal to 1 AU in length, and so the angle is 1 arc second, and so the radius of this circle is what is going to give you 1 parsec. And plugging in the values here, we can obtain that 1 parsec equals approximately 3.086 into 10 to the power 16 meters. And now to sum it all up, here are a few conversion charts which can come in handy while solving problems. So here's the one for length, you can go through that in your own time. And we can have a chart for the units of mass. So most of these you must be familiar with, and the Chandrasekhar limit is the maximum mass that a stable white dwarf star can have. And lastly, we look at a chart for the units of time. Again, these are all familiar units except maybe for the last one, which is something that was important in atomic and nuclear physics. A shake, which is the time taken by an electron to jump from one orbit to another. And that brings us to the end of today's video. So to summarize, we looked into physical quantities and their different types based on the two types of classification. We looked into dependent and independent sets of physical quantities, units of measurement, the different systems of units. We also looked into the 7 fundamental SI units, supplementary units for the solid and plane angles, unit prefixes, and lastly some special units and conversion charts. In our next video, we are going to start with solving some problems on unit conversion, solid angles, before we go into significant figures, uncertainty in measurements, and lastly types of errors. So stay tuned and keep learning with us at Eigen Akademie. See you in the next one.